Hello, good morning, everyone, and welcome to another installment of the EDIAQI webinar series. It's been a little bit of a hiatus, but let's jump right in because we have an action-packed agenda for you guys today. First things first, housekeeping. So please, audio and video settings. Please make sure your video is off. Please make sure your cameras are off and your microphones are off. This webinar is being recorded. So please, if you don't actually want to be filmed, make sure that your camera and microphone are off. Presentations will be shared after the webinar. And please ask any questions you can. This is an open discussion. And we want to hear your voice, your ideas, and any questions that you have. And obviously, if you'd like to use captions, please kindly click on more than language and speech, where you'll find an option to turn on live captions if that's easier for you. So let us begin. Well, according to the WHO, poor indoor air quality is one of the biggest global health concerns, with over 90% of people living in areas that often exceed safe pollution limits. In fact, according to the EU, poor air quality is the largest environmental health threat in Europe, contributing to a significant number of deaths each year, 239,000 to be exact, from exposure to fine particle matter. Understanding the full picture of health risks posed by pollutants requires monitoring and assessment, and that in turn requires equipment. However, traditional air pollution monitoring equipment is bulky, expensive, and requires skilled technicians to maintain. Low-cost sensors offer a potential breakthrough, enabling more extensive studies on air quality, particularly indoor air quality, a critical concern as people spend approximately 90% of their time indoors, where pollution levels can often be significantly higher. However, I was going to say LCSs, which is the acronym, come with both advantages and obviously limitations, and a clear understanding of their capabilities is crucial for employing them effectively. To explore these critical aspects, In Child Health and EDIAQI presents the latest installment of the EDIAQI webinar series, which will address the following key questions. What are the main advantages of low-cost sensors compared to traditional monitoring devices, and how does their effectiveness depend on specific environment in which they are used? What are the limitations of low-cost sensors, and do these constraints inhibit their deployment in certain contexts? At the end of the day, do low-cost sensors offer value to buildings and, more importantly, to occupants? So let us dive right in. So joining us today for this important discussion, we have Sotiris, a dear friend of mine. I'm not going to try to pronounce the surname because I butcher it. He's the lead author of the Global Air Quality Standards, GoAQS, and he's a very well-known member of our community. Also, Dr. John Saffold, the director at Nosmotech. He's had a little bit of a delay today, but he will be joining us very, very soon. And Dr. Lila Diapoulou from the In Child Health Project and also a researcher at Demokritos, based in Greece. And a dear colleague of mine, Mr. Jan David Foster, researcher at Leipzig Institute for Tropospheric Research. So let us take a quick run through of the agenda. Well, I've just done the welcome and the introduction, so I don't need to say that again. Then we'll look at the science and challenges behind low-cost sensors, then technological developments and market trends in IAQ monitoring. We might have to shift that a little bit, depending if John is able to make it sooner. Technological developments and market trends in IAQ monitoring, advantages and disadvantages of low-cost sensors with Lila, bridging science and usability, a novel user-friendly approach to particle size distribution in indoor air with Jan, and then finally panel discussion and questions. But please, any questions you have, ask at any point. We'll be creating a reserve of questions to ask the panelists during this portion. So with that, I'll stop. I'll hand over the floor to my dear friend Sotiris. The floor is yours.
Alex, thank you so much for inviting me in this fantastic webinar. I really like technology, and I would like to share a little bit more of how I see things and how some of the challenges that we have specifically with low-cost sensors, but also some pros because they do offer us some valuable information. So if you can please go to the next slide. So currently, we use reference instruments in order to do epidemiological studies when it comes to different pollutants. And for that, we do have very expensive equipment that should be deployed in specific locations with specific conditions, and a specific person should be there in order to monitor and operate the devices. As you understand, those kind of devices, although they provide you the absolute measurement, the cost of operation is super high. So something that creates a barrier when it comes to putting those instruments inside a building and trying measuring what's happening in the indoor space that, as Alex mentioned earlier, we spend the majority of our times. For this reason, lately we rely on those cost monitors that they help us see different pollutants and quantify them in order to take the appropriate measurements, if you like. Next slide, please. So in many cases, I see some confusion when it comes to some terminology, and we use low-cost sensors for the bare electronics, and we use low-cost monitors for the final product that consumers or researchers will buy in order to monitor air quality in the indoor spaces. So LCS is for low-cost sensor and LCM is for low-cost monitors. Next slide, please. One note here, it's very important to understand that low-cost sensors and low-cost monitors, they are not calibratable. We cannot calibrate. And the reason is, if you can change the slide, please, because they do not follow any guidelines, any standards, especially the sensors that we buy from the manufacturers in order to build the monitors. They don't comply with any standard out there. There are some standards, like for example, here we have the ISO standards for particle counter devices or sensors, if you like, and they have to follow specific thresholds inside all of those different categories that they have to comply, like what is the size setting error or the count efficiency, the size resolution, if they can count false particles, etc. Something that we don't have currently, although not all of them, but the majority of the low-cost sensors, they do not comply with any standards currently. Next slide. And the reason they don't comply is because the manufacturer of the sensors, they don't disclose openly the algorithms that they use in order to calculate different pollutants. If we look into the PM sensors, for example, they have a baked algorithm with statistical estimations aerosol models in order to convert those particle counts into mass, which is the final number we use in general in order to understand if the air quality is good or bad inside buildings. And those algorithms, they are unchangeable and unknown. So basically we call them black box for this reason. And even the manufacturers that or integrators that they take those sensors in order to make the final products, they do not have access to this kind of information. So, and something else is happening though. The manufacturers, as they would like to offer better products at the end of the day, they use machine learning algorithms and some techniques that they are called normalization or harmonization of the data once the measurement is taken. And then they provide better data based on those different algorithms that they have implemented on top of the sensors. Next slides, please. Next slide. Okay, so here are some pros and cons. No, go. Thank you. So here are some of the pros and cons by using low-cost sensors in the indoor space. Pros are that we have better spatial coverage and also temporal coverage because of the price. Something else that we are exploring currently is that air quality sensors or monitors that they are deployed in the indoor environment have even more precise image of what's happening and the air pollution exposure individuals have, rather than relying on outdoor reference air quality stations, because they are maybe in 5 kilometers distance and they are not going to give you the exact concentration of particulate or any other pollutant in the indoor space. Another benefit is that they have a silent operation. They don't make any noise. They don't require lots of energy either. And also those devices, they can hooked up with the building automation systems. So basically, if you have an HVAC system and you want to control automatically when you need more ventilation or less, those devices can communicate back, and the user has very little implication with all of this process. Of course, the cons, as we have seen, is the lack of standardization with most of the sensors, although we are having advance in that area. They cannot be calibrated, remember, but we can harmonize or normalize data. For that, researchers or manufacturers, they do evaluate the sensors, and they go a step further by analyzing and comparing data between reference stations and those low-cost monitors. Environmental factors like humidity, for example, may affect some of the sensors, so we have to be aware of that. And the lifespan of the sensors in some cases is unknown, especially for gas sensors. Particulate matter sensors in general, they have a very good lifespan between 5 and 10 years, and also it depends the amount of pollution that they are exposed to. Next slide, please. Here is an example of advancements that we are currently have in the space of TVOC sensors, the total volatile organic compound sensors. So as you can see on our left side, we have 3 different sensors from the 3 different manufacturers. And all of those sensors, they measure some common VOCs, but also they may measure some different. And another problem that they are facing is that not all of them, they are measuring the same pollutant the same way. So in some cases, like sensor number 3, it may give us more concentration, higher concentration for a specific gas. In that case, I didn't mention the name of the gases, but I mentioned, I created analogies with fruit, which I think we can understand them better. So another example will be on our right hand, where we can see 2 different sensors from the same manufacturer. And basically, this is a PID sensor, a photoionized sensor, which uses some lamps that emits ultraviolet light in order to excite some of the particles or some of the gases and be able to measure the concentrations of the different VOCs. So based now on the lamp that they have embedded, they may be able to measure some or more VOCs. And at the end of the day, the end user does not know what kind of a lamp is inside this specific sensor. So for this reason, we need some kind of collaboration and create a standard around it, which is happening currently. And hopefully in a couple of years, we will have a standard where all TVOC sensors are going to provide the same amount of information for the total VOC number of a pollutant. Next slide, please. And that's all. Thank you so much.
Thank you, Sotiris, for that very accessible dissection on what low-cost sensors and low-cost monitors are. I've actually learned that today because sometimes I use them interchangeably as well. So thank you very much for that really clear distinction there and what they actually mean. Now we're going to head to John. I think that we had a little bit of connection issues on his side, but he is here and with us. John, please come in, take the floor.
Yes, thank you very much. I'm having trouble. Unfortunately, Teams won't allow me to display what anyone's showing. So I'm not quite sure how we're staying synchronized on this one. However, I propose the following, that I'll ask you to change slides, and I'll change slides at the same time as you do.
Perfect.
Okay?
Absolutely perfect, John. Thank you. Could you turn on your camera for us, John? Could you turn on your camera?
No, the camera will not turn on. I'm having trouble with Teams.
At least we have you here. That's the most important thing. Take it away, John, and hopefully we'll do it coordinatedly.
We will certainly do that. Okay. Thank you. Okay. Right. What we'd like to discuss here is the basic technologies that are available for low-cost sensors. And on the first slide is a quick summary of what we're going to chase. We're going to chase 5 technologies: NDIR, electrochemical cells, laser scattering for particles, PM, metal oxides, and PIDs. And up in the right corner is a picture of the first thing that anyone has ever did with low-cost sensors. That was 20 years ago. We're on our 20th anniversary of low-cost sensors. This was sensors that at AlphaSense we put into a system for a project called Message, run by Rod Jones and the people at the Cambridge Atmospheric Chemistry Group. So that was the first time LCS were used, was 20 years ago. Next slide, please. NDIR, as we know, is used for carbon dioxide, and the very first people were Telair back in the 1970s, producing relatively low cost. These days we have LED IR sources, and what's happened? Well, the power has gone from 200 milliwatts to less than 200 milliwatts. In fact, a couple of days ago at Nuremberg, I talked to EDIAQI and MIPEX, and they're now operating at 0.2 to 0.3 milliwatts. The cost has come down from a couple hundred to as low as $20, perhaps $70 for a CO2. And the accuracy, regardless of what people say, it's hard to be better than about 50 ppm at about 500 ppm CO2. To go much better, you end up there is some problem. Just a second, we're having a problem with the slides here. Can I have the right to present?
Yes, please go ahead, John. Take it away. Take it away. As this seems to be an issue on my side, please do take away and just upload. I'll stop presenting now, and please do upload. Some complication here today. Thank you.
Yes, yes. Well, we're just having fun here, aren't we? Okay. Screen. Right. Can you see my screen?
Yes, John, we can. Yes,
is my screen available?
Yes, yes, we can.
Okay, let me just go over to, just trying to get over to pre-presentation mode here. Okay, there we go. Okay, can we see the slide now?
Yes, we've got it. Perfect. Absolutely perfect.
Okay, okay. So in NDIR, you can see that there are a number of gases that can be measured, focusing on CO2 because we're looking at IAQ and ventilation, and we're working around 50 ppm. And what do we have in the future? Well, there'll be new sources called plasmons, mid-IR LEDs, and lasers are now coming down quickly in price and becoming available. Other gases, ammonia, nitrous oxide, methane, CO, they are available or will be available at the same cost as CO2 eventually, and the housings are shrinking. Right. Amperometric electrochemical cells. Those are the most commonly used for measuring our gases, the inorganic gases. And they've been dominating the safety industry since the 1970s. And literally anyone who goes into a confined space anywhere on this planet is probably using an electrochemical cell for oxygen, carbon monoxide, H2S. And the electrochems operating at ppb since 2005, as I said earlier. They don't need any power, but the op-amps driving the potentiostat circuits need the power. So the power requirements of amperometric is up to your electronic designers. You either have really low current or really low noise. You don't get both. And the cost for sensors is $15 to $75. In volumes, they tend to be around $30 to $40 each. Lifetime is 1 to 10 years, and the lifetime doesn't depend on the manufacturer. It depends on the catalyst they're using. The noble metals like platinum last a long time, and some of the catalysts like the carbons don't last as long. So the lifetime really depends on the type of sensor, and any manufacturer says all the catalysts have this, all their sensors have the same lifetime is incorrect. Accuracy, well, currently people can get a root mean squared error of about 3 ppb in the area we're interested in for NO2, around 0 to 50 ppb. In the future, for electron sensors, they're around, but they need to be understood. CMOS processed electrochemicals by people like Sensorion will drive the prices down. We do have 4x4 millimeter sensors now available. There's a picture of one in the corner, and pretty soon, people are starting to add micros onto the sensors themselves and doing edge processing to do some of the temperature and other humidity corrections. Moving on, let's move on to particles. You probably all know the particle monitors, such as the Plan Tower, etc. There are two types of particle monitors. There are the nephelometrics. The one on the left is a picture of the Terra Next PM, and that is called nephelometric. It just measures how much everything is scattering. Whereas the one on the right is an optical particle counter, sometimes called a particle spectrometer, and that measures each particle as it goes by and gives you a distribution of the particle sizes. The one on the left gives you a broad measurement. Is much more expensive, but gives you specific profiles of the particle sizes. They've been around, low-cost PMs have been around for about 15 years now. They all have similar powers. They all take about that sort of the area between 60 and 200 milliamps. You can get an nephelometric for as cheap as 15 by an OPC optical particle counter for anywhere from $150 to $400. Lifetime, it depends. The lifetime is going to depend on the laser and the fan, and 5 to 10 years is not unrealistic. Particle accuracy, they always specify PM 2.5 because that's what we calibrate to and that's what we know. And they happen at PM 2.5 for the people who are doing what's called PM1 and PM10. The bigger and the smaller ones are normally estimated from nephelometric from what they read on the 2.5. In the future, the optical particle counters need to come down in price. We need to correct for humidity. It's an important correction that people are now getting their heads around. What we really want is to measure those ultrafines. Those are the really small ones that are invisible. And those are the ones that are toxic that we just cannot afford to measure. And also, it would be nice to know what the particles are made of. Is it soot? Is it something really toxic? We just don't know. Metal oxides. You will find these in frequently in the things that are sold on Amazon because they're cheap. Up $3 to $10, maybe even up to $40. They take a little bit of power, 10 to 500 milliwatts. On what are called micro hot plates. And they've been around for 15, 20 years now, but the actual idea of a metal oxide has been around since the 1960s by Taguchi and people like that. They're excellent lifetime. They'll last 5 to 10 years. And where you don't care about accuracy, they make numbers that go up or down. So be very careful of any accuracy specifications by any manufacturer of metal oxides. The phrase spurious is my being polite. In the future, we'll mix the two types of semiconductors, both P-type and N-type. We'll improve the chemical filters so they can be more specific. Again, there'll be better what's called, ML on the edge. And there are advanced material scientists doing some advanced heterojunction work in metal oxides. And if you like, the gold standard for low-cost sensors when measuring VOCs are the PIDs, photoionization detectors. There used to be only 2 manufacturers. There are now about 6 or 7 at Nuremberg the other day. So it's becoming a more popular method. It's more expensive. It's $250 to $500. But what's good news is the lamps now last a long time, 5,000 to 10,000 hours. The accuracy is kind of odd because you calibrate with isobutylene when you're measuring a VOC, but in reality, each VOC has its own constant, its bias or coefficient, whatever. So there isn't any universal way of getting the exact VOC you want. You get what a generic VOC measurement with PIDs, but they do go down to subparts per billion now. The prices are going to come down because some critical patents have expired. Most lamps are what's called 10.6 EV, but now 11.7, which let us measure a lot more things, are now finally becoming reliable. And the humidity issue, which has always been a problem with these, has now been corrected. We've been talking about price and new technologies, but let's remind ourselves what we really want is good data quality. And so how do we validate these low-cost systems? Well, people have been saying there are no standards around, and actually I have up here 4 standards that I have worked on with other people at both ASTM, CEN, and ISO now. And all of us have been producing standards for particle monitors, for gas detection, and ultrafines as well. Some of them are going through approvals, others are already out there. And there's a group, SEN 264, Working Group 42, we have just been funded for 800,000 to take our technical specification, it's not a standard, it's a specification of 17660 to become a European standard. And in true European style, it'll take us 3 or 4 years, but eventually 17660 will become the standard for validating outdoor air quality low-cost networks. And of course, ML, AI, and neural nets are going to help the accuracy, but as a chemist, I beg people, don't go straight to ML. First, please apply the underlying chemistry and physical corrections that you know about, the humidities, the interfering gases, the things that we know about in temperature. Let's do that correctly before we start applying our ML. And that is the end of my presentation. Thank you very much. And I'll quit sharing.
Thank you very much, John. I've certainly learned a lot from that. It was a dissection of everything low-cost sensor-wise, from all the different particles to all of the different devices and particular parts of the technology to measure. I'm much wiser, so I think I'll take a deep read of that. We might need a second just for the presentation to load now. And I'm going to hand over the floor now to our sister project and friend, Lila from Democritas. Lila, the floor is yours if you already want to start saying some words while the presentation loads.
Thank you. Good morning. Very happy to be here. Many thanks for this invitation in this very interesting webinar. So I'm Lila Diapouli from NCSR Democritos in Athens. And I will talk a little bit about advantages and disadvantages of low-cost sensors for children's indoor environments. So we can move to the next slide. Is it move? Oh, yes, perfect. Thank you. So let's first talk a little bit about children. Why are we interested in children and children exposure? So we know that children are more vulnerable to air pollution. And this relates to their bodies and organs and immune systems still developing, but also to the air that they take into their bodies. So because they breathe faster, they take in more air with respect to their body mass in relation to adults. So when we want to assess their exposure and the risk related to this exposure, what do we have to do? We have to know where they are, so where they spend their time, where they breathe this polluted or not polluted air, and how much time they spend in these environments and how clean or not these environments are. And in this in the right-hand side, you can see some results from a previous project where we have the time spent by elementary school children. Thanks, Alex. In Lisbon. So these are patterns that students have reported themselves. It was above 100 to 200 students. And we see, as we expect, that the home is one of the most critical microenvironments. And then we also have the school microenvironment, which is very interesting. And we also get some transport microenvironments that can be of interest because we know that the levels are increased there. And some time spent outdoors. Children tend to spend more time outdoors than adults. We can move to the next slide. Next one. Thanks. So when we want to study children exposure, we usually try to assess air quality in these critical microenvironments, and mainly these exposure studies focus on homes and schools. And these are microenvironments that have specific features and specific requirements for monitoring. So, of course, what we need to do is monitor regulated pollutants because we want to assess compliance with outdoor standards or also with indoor guidelines when these are available. So we want to measure PM in different size fraction and some key gaseous pollutants. But also we may be interested in specific other pollutants that are related to outdoor or indoor sources. For example, we may want to check tracers for traffic like black carbon, or specific indoor activities or building materials or furnishing that may emit specific chemicals. Another important part and need is the high temporal resolution of this data. And this relates to the indoor sources, because indoor emission sources may be of short duration. So we need to have this high temporal resolution in order to be able to catch them. And also we need to think that these exposures that we want to assess in these different microenvironments may last for smaller periods than 24 hours. That is like a typical averaging period. So we may be in a transport environment for some minutes, in other environments for some hours. So we need to have this variability in the concentrations of the pollutants. And lastly, but also very important, is we need to consider that these are indoor spaces where people are living or working. So we need to cause as little as possible nuisance to these occupants of these spaces. And we need also to be careful of the airflow rates of our monitoring devices, because these indoor spaces have low volumes, especially if you compare them to ambient air. So if we are monitoring we do active sampling and we have high flow rates, we may alter the indoor airflow. So we may alter the indoor conditions. And we have different real-time instruments that we can use that can cover these requirements. And this can go from reference or equivalent to reference to low-cost monitoring systems. We can move to the next slide. So how do we choose? How do we decide if we can go for reference grade or low-cost monitors? We need to understand, of course, the advantages and disadvantages. So low-cost monitors, the most obvious advantage is their low purchase and operating cost. So in this case, we can study many sites simultaneously. So we can cover all types of microenvironments and related exposures, which is very important, of course. They provide the real-time data with high temporal resolution that is needed for indoor environments. They have very low airflow rates, so they cover also this requirement. And they don't cause nuisance in general. They're very small and noiseless. And what is also very interesting is that some of these systems, some of these monitors are connected to online platforms where you can see the data immediately. So the data are available through web or mobile applications. So you can have an immediate access to the data. And an example is the lower part, this picture of the lower part, which is the platform that we collect and show the data that we collect with our system, their Sensi system. And also, some of these devices can also be portable. So they are light, they have energy independence, so they can be used also for mobile applications, and this is also very useful for exposure studies and for citizen science studies. And you can see in the right-hand side a picture of their Sensis device in its mobile form. So it can be worn by children in our case, because we are, of course, our project is studying children exposure. So we can move to the next slide. So many advantages. Can we really then use only low-cost monitors? Can we substitute reference grade instruments with low-cost monitors? There are also some disadvantages that we know. So we know that there are still problems and issues with precision, with accuracy of the sensors, and also with long-term drifts. So the long-term use, you may see that the performance is decreasing. We know that for some sensors and for some parameters, you can only get qualitative information. You cannot really trust the quantitative data. Another issue for indoor environments is that sometimes the levels indoors may be below the detection limits of some sensors, especially for gaseous pollutants that are emitted outdoors. You may find very low levels indoors, and then maybe your monitoring system, low-cost monitoring system, cannot catch actually these levels. We have seen, of course, through all these applications over the years, that there are problems with atmospheric conditions. For indoor environments, sometimes it's better because you have more stable conditions for temperature or relative humidity, so you may have less effect, but still we know that this is a problem and we have to consider it. And of course, they are not available for our air quality parameters that we are interested in. So my quick take-home message from developing and also using these sensors for some time now is that these low-cost sensing technologies really offer great opportunities, especially for exposure studies and for indoor environments, but we have to know how to use them. And we need to have standardized protocols for continuous evaluation, not calibrating once and then feel that this is okay for many months or years, and also continuous calibration of these devices. And actually, I was very happy to hear from John from the previous talk that this is something that is already underway. So with this, I would like to thank you. And I'm really happy to contribute to the discussion that will follow.
Thank you so much for this great presentation. Really interesting to see the work that you're doing on low-cost monitors, and particularly in regards to children. And I like the flow as well. I must say that it's flow because now we're going to keep flowing even more so with Jan David, who will actually now talk about our calibration pilot and specifically the monitors that they are creating. So Jan David, please come in. The floor is yours.
Yeah, thank you so much for the kind introduction, Alex, and thank you for having me as the surprise guest today. And yeah, today I'm excited to introduce AQB. It's a new measurement platform designed to sort of bridge our scientific curiosity with the real-world usability. And it will allow us to measure and understand indoor particle pollution in a way that it's both research grade sort of and also accessible to the end user. Next slide, please. So when it comes to indoor air quality sensors, or especially particle measuring devices, we have a set of measurements usually, like PM1, PM2.5, PM10, CO2, nitrous oxides, volatile organics, whatever that value means. We had that before in John's presentation. And in the EDIAQI project, we want to go a little bit further, and we want to really make use of the data. And one of our main goals is to actually measure children's exposure to air pollution, and then to model the lung deposition, which requires detailed information about the particle size distribution. So the mass concentration, the total mass, is just not enough to accurately model this in subsequently. And that's why we recently decided to launch a new measurement campaign and to also build a new measurement device focused specifically on capturing high resolution particle size data, temporal and also size resolution wise, in indoor environments, in children's playrooms, and also maybe kindergartens and schools. Next slide, please. So there you see a typical size distribution. And for our lung deposition modeling, knowing the exact size range and the number of particles is really essential. This means that we need sensors that can detect and classify individual particles, and ideally in real time and under realistic indoor conditions. Next slide, please. And we also heard before from John that most particle sensors on the market follow two main working principles. On the one hand, the nephelometers shown on the left, they measure. So I had the AI somehow hallucinate here some nice pictures to illustrate how these sensors look like. I think I'm not going to show the actual devices. We saw them before. So what the nephelometer does, simply spoken, is that they measure the turbidity. So you have a light scattering signal and a general idea how turbid the air or the fluid in general is. But these nephelometers, they don't provide detailed size or count information. They are pretty common in commercial air quality monitors, but they are not suitable for our needs. And that's why on the right, we wanted to go with optical particle counters to detect individual particle sizes. And this is much closer to what we need for the lung deposition analysis, as we also learned that the nephelometers only basically provides, or the scattering somehow gives you an estimate of the PM2.5 value, but the PM1 and PM10 values are then calculated based on several assumptions on conversion factors, and this is actually not enough for us. So on the other hand, the real optical particle counters, they are often not so low cost. So I don't know, a tenfold of a nephelometer type sensor, for example, when you compare these. And yeah, and their performance, on the other hand, they are also cheaper optical particle counters, but their performance is pretty poor. And yeah, still you make some assumptions with the optical particle counters. And that's why sensor selection, comparison, and calibration of these sensors is pretty critical also for our part of the campaign. Next slide, please. So you might ask, why don't we just use an existing commercial air quality monitor, some of which we just saw? And the most simple answer is most of them are closed systems, and they are often expensive and not modular, and they don't give us access to the raw data and the algorithms behind the numbers. And this makes it unsuitable for our research needs. Yeah, but at the same time, we also didn't want to build like a typical scientist-only prototype, something complex or bulky and hard to use, which you see here in the lower left corner. And that's why we need actually your input from the audience, that because after the webinar, we invite you to take a few minutes to fill out a questionnaire. And I don't know how the questionnaire will be provided. Alex will give some detail on it.
I'm very excited to let you know that I created a QR code, a dedicated slide. So get ready, guys. You get to really engage with us live. Please, yeah, take back the floor.
Perfect, Alex. Thank you so much. So everything is set up already. So this questionnaire will actually make sure that, or your input will help us to check whether we are working in the right direction with our development, and it ensures that the device is not only technically sound, but also something people actually want to have in their living spaces at schools or kindergartens. So your feedback is really valuable, and we appreciate your participation. And please go to the next slide, Alex. So the device we are currently we thought of is this here. I can show it into the camera here, so it's so you have an idea of the actual size. So EDIAQI is called the Air Quality Beacon and Emission Evaluator, and EDIAQI stands or is a platform basically it's pretty flexible. It's an open platform that's both scientifically reliable and user friendly. So it can hold various low cost PM sensors and also an OPC. So it allows to run multiple sensors in parallel, nephelometers versus OPCs, under identical conditions. So we constructed a common inlet system so that basically all the sensors see the same air mass. And because it's open source, we can, of course, calibrate it and do comparisons and run the system in our reference laboratory. And also the interface we designed, so it's everything from scratch basically. And Yeah, next slide, please. Yeah, so this is already my last slide. So this showcases again that our EDIAQI system is designed to integrate smoothly into the real world environment. So you can access the data via your phone on the one hand, but the data are also with high time resolution logged to an SD card for subsequent offline analysis in case you don't have internet connection at the moment. And on the other hand, we can also have real-time access to the data. So the data are transferred via the MQTT protocol. It's an industry standard Internet of Things, IoT protocol. And so we can, from all the devices, see actually what they are actually doing, what the status is. If there is some defect, we can upload remotely even software update or the new set of calibration values and so on and so on. And it also comes, it can also operate offline, I have to say, and it comes also with a battery backup, so you can take it with you and it runs for 1 day unattended without having to plug it in into a socket. Yeah, so that's actually my short introduction. I was told to keep it short, but I'm happy to receive your questions.
No, really fantastic. You're all very short. You had a lot to say. Not going to, I wasn't the best timekeeper. We've gone significantly over, but I just kindly ask all of our speakers if they could just stay an extra 10 minutes so we can really answer everything. And for the panel discussion, if they could kindly keep it short, but obviously sweet as well. So let us go ahead, and we're going to start with my dear friend Sotiris. Yes, Sotiris. How do we balance the affordability of low-cost sensors with the need for precision, especially in high-stake environments?
I think from all the presentations today, we understand a little bit better the challenges that we have around low-cost monitors and sensors. Like what Evangelia said, like if we calibrate frequently the sensors, the monitors, in order to comply with those standards that may be present in the future or we already have, it's going to ensure that those low-cost and affordable sensors are going to continue doing a fantastic job when it comes to informing us about the air quality inside buildings.
Thank you for being very short and sweet there. Now, John, if you'd be so kind, what role do certification, accreditation, and validation play in ensuring credibility of low-cost sensors?
Yes, thank you. The thing that's stopping us from accepting low-cost sensors is our trust in the data. And we're relying on technical data sheets from manufacturers to often convince us that the data is of good quality. And having been at AlphaSense and started AlphaSense 30 years ago almost, I know how technical data sheets are written, how competitors write technical data sheets, and there are a lot of opportunities for exaggeration and the salespeople intervening. Therefore, we need a third-party way of doing it to build that trust. And the only way that we all out there, as the consumers, the purchasers, and the users, will trust data is if we can see that there's a certification. We're used to EN and CE stamps. We're used to UL. We're used to it, and we don't see it yet in low-cost sensors, but it is coming.
I have to now do a point out to my friend Sotiris here, who's working on this, on creating global air quality standards. This is an excellent example. Obviously, the work that we're doing at the Ideal cluster and the project is all open source, and we need to do it together as a community to kind of decide these things. So thank you very much for making that call as well. John, Leela, please, what role can low-cost sensors play in assessing and mitigating risks for children?
Well, as we discussed a little bit before also, low-cost sensors are the way they are built, the way they are very small and easy to operate, but also to install, are perfect for indoor environments. But for me, the biggest advantage is their low cost. So if we think that if we use a reference grade instrument, we will have a minimum cost of, let's say, 10 to 15,000 euros. So you can understand that the number of microenvironments you can study is limited by the time of the period that you can do the study. You cannot have many parallel microenvironments measured. Then you have a very big advantage using low-cost systems where you can actually deploy a dense network. So even considering their limitations, and even if we rely for some parameters only in quantitative information, being able to have even this information on indoor air quality for multiple locations, for example, inside the public building, a school, or in many homes, I think this goes a long way towards managing indoor air quality and mitigating exposure risks, especially if you have IoT systems where you can have immediate access to data. So you can have non-experts, parents or teachers even assessing the risk exposure and maybe also taking corrective measures if this is needed. Another very important aspect of these systems is also that they are ideal for citizen science studies. So I think this is also something that is a big advantage for the systems, that you can actually use a lot of them, but also use them, give them to citizens. You will not give an expensive, high precision instrument to citizens, but you can give many, as we did in child health. We distributed 20 portable low-cost sensors to students. So because of their low cost and easy way to use, you can do these things. And I think that they are really, the applications will be increasing. So what we need to do is make sure that we understand how to use this data, either qualitative or quantitative, and we can really get very good, let's say, we can help in terms of assessment and mitigating risk for children.
Thank you for that very interesting look. And I very much like the fact that the advantage is the low cost nature itself, right? That is the key advantage. So I think it's something very important to highlight there, where instruments sometimes can cost, I think, up to 10,000 euros. So very important point. Jan, please, following on from that, what measures are in place to ensure consistent data quality in varying indoor conditions, such as changes in humidity, temperature, and household activities like cooking?
Yes, that's actually something we paid a lot of attention to. So in indoor environments, we heard from various talks that the environments can be quite dynamic in terms of humidity, temperature, cooking has an influence. So with our AQB device, we use a common inlet to run multiple sensors, low-cost sensors and not so low-cost sensors side by side. So this way we can compare them directly, and we can catch things like individual sensor drift or outliers when conditions change. So we also always log the temperature and humidity and some other parameters alongside the particle data that we are collecting. And so we can put everything later on into context, and if needed, correct the data afterwards. The data are continuously logged with high time resolution. And in the post-processing, we, of course, will then apply machine learning-based corrections. But we also know the science behind it. Maybe you know that here at Tropos, there's the World Calibration Center for Aerosol Physics, where you can calibrate all of these sensors in comparison, do intercomparisons to reference instruments and calibrate them to reference grade OPCs and so on in our reference laboratory. So that's how we are tackling this challenge.
It's a big challenge indeed, and we're doing some great work here at EDIAQI and at Tropos. Now I asked my panelists to be even shorter and sweeter as we are running close out of time. So please, Sotiris, what advances are being made in sensor technology and data analytics to improve low-cost sensor reliability?
I think we already mentioned, but some advantages in general in sensor technology is that right now we rely on those, algorithms in order to see even beyond PM values when we talk about particles. And we can see, for example, based on their size, we can estimate the source of the problem, which can help us, remediate the problem at the end of the day. And if you allow me, I would like to add something on the previous question that you asked, Jan. Um, in the indoor space, we talk about humidity as something that may affect particulate matter sensors, but in reality, I think that humidity, aerosol, particles that basically are water may carry some of the pathogens out there. So I'm not sure if we should, exclude those measurements when high humidity is present. We rather, I think, we should move beyond measuring particles of mass and looking at the sizes. It's more relevant to the future. I think we have an understanding better the effects of those different sizes and combination of, the chemistry of the particles on human health, rather than relying on solely on mass. That's all.
Jan, you have to come in and now respond to that. I give you an opportunity, maybe just for your 2 cents in the comments there as well.
I fully agree. So
collaboration at work, yeah, collaboration at work, which is what we're always going for. John, please, now, what are the key barriers to preventing the widespread adoption of low-cost sensors, and how can these be overcome?
Oh, what a simple question. Well, first of all, on the humidity, I absolutely agree that we need to measure the composition of the particles and not just the mass. I mean, if we ever did that with gases and told you that there was 2 ppm of toxic gases, you'd want to know what they are. Is it CO or formaldehyde, or NO2? You just need to know it. We don't know that about particles. So that was my first side comment. What are the main blockages? It isn't price. I think price is now becoming reasonable. It really comes down to people trusting the data quality, and the one that is going to become more of a problem is transparency, especially with people applying ML and AI to the data. The traceability and the transparency of the data is going to become a bigger problem as we get more complicated trying to calibrate. We're going to also more obscure the traceability of the data. So that's going to be a problem. But right now, it's people trusting the data. And whether we use R-squared or RMSE or whatever we want to use, that is also the perception that these sensors die and they don't last very long and they aren't very good. It's a perception problem more than a reality.
Thank you, John. Very interesting nuance. Look at that. It's more about the way, it's a trust issue in many senses. I think it's been quite a big point you've made. Leela, please, how do behavioral measures and citizen science approaches enhance the effectiveness of IAQ monitoring in children's environments? And I think that point of citizen science and this participation of children is something close to my heart. So just to commend that.
Yeah, this is actually a very interesting question because I think it actually goes both ways. So you can also think about it the other way around, how indoor air quality monitoring under specific conditions can also motivate citizen science activities and behavioral changes. But this aspect of involving citizens in indoor air quality, which is very much linked to low-cost systems, so they are the most friendly systems to use in this type of activities, it's something that I think has a lot of future. If you think about it, citizens that are have environmental awareness, so they're willing to change their behavior, their habits in order to promote environmental protection, they can be the basis actually for citizen networks. They can accommodate devices in the areas they work, they live. It can be indoors or outdoors, but they can also be responsible for these devices. They can make sure they operate, they check the data. And this type of devices, as the local system we're talking about, don't really need experts to do that. In the case of children exposure especially, the active involvement of citizens, being students or teachers or parents, is even more critical because this indoor air quality monitoring involves getting in places where people spend their time, sometimes private areas like houses. So these people need to understand the importance of monitoring these sites and support the installation and the operation of the sensors. In addition, we want them to provide us data about the indoor activities, what they're doing, the daily patterns, the ventilation practices. And these are very important to have together with the measurements. So we want the collaboration. So we want this type of activities, of citizen science activities and behavioral measures and behavioral changes to go together with indoor air quality monitoring. But if we think about it in the other direction, think about how this monitoring with, especially with IoT devices, where you can have the information in a nice way, nice visualization tools, and you are a non-expert, but you see the problem. And when you see the problem, and also you're given the opportunity to be actively involved in monitoring the problem, I think then you tend to be more active also in solving it. And these type of activities are where low-cost sensing systems can be really, really useful.
Jan, very short and sweet, if you may, as we're almost at the end and we have lots of questions to get to an extra 10 minutes.
Yes, so coming to the question, I think I can make it really short. This is something that we are going to learn in the course of our campaign. And we are going to learn about how the sensors are affected and what the inaccuracies are. And the idea is that through the long-term measurement, we are planning currently a 2-month measurement in one room with one child, with one device. And then we can really get a comprehensive set of data and do a sensor intercomparison so that we can better understand and correct for the accuracies. And yeah, so on top of that, we also want to calibrate all the sensors beforehand and afterwards, and then we see how the interferences and what the limitations are and how the sensors drift and how they degrade maybe over time. So that's my response.
Very eloquent response, and I hadn't even asked the question, so apologies there. I realized not very good moderating by me today, but very good answer. Okay, guys, so we're going to jump straight into the questions now. If you have any more questions, now your chance, ask them quick because we're running out of time. We have a really long list. I'm actually going to start with the last one today, and I think this is for John and Jan. Are there any independent labs that provide bump testing service to check accuracy of consumer-grade gas and particle sensors? So maybe start with John, then go to Jan, and then Sotiris and Lila might have some points here as well. So please, John.
I wish there were. The problem is, in fact, we're confronting this in my working group 42, in that labs are reluctant to do this type of testing because of the expense of meeting ISO, was it 17025, or the specification to be a test laboratory. It is quite onerous for good reasons, but in being that onerous, it's made the cost so high and the burden so large that labs are not willing to go in that direction. I wish they were.
Jan, please, and then actually Sotiris raised his hand. If you jump in, please. You must have a burning point here.
No,
yeah. So,
oh, please, Jan.
Jan, go ahead.
Okay, well, I quickly take it. So at Tropos, we have actually a reference laboratory, the WCCAP, the World Calibration Center for Aerosol Physics. But of course, we are somehow limited in the time we can spend on retesting. So we do it occasionally for, or pretty regularly actually for companies to test their research grade devices, and we really want, we also adhere then to the standards and check the accuracy of these devices, but that are not consumer grade devices, so that are really research grade devices. So we cannot provide the service for like a whole set of consumer grade low-cost devices, but also in the course of the EDIAQI project, we did some intercomparisons and checks, and we will keep doing it in the future.
Thank you, Jan. Sotiris, jump in, please.
Indeed, there is an organization that do some kind of evaluations. It's called AQSpect. They are located in the US, in California, and they do field and laboratory correlation of low-cost sensors against the reference instruments in order to see how well they operate. And they share all this information openly and publicly, so everyone can go and visit their website and find more information about the devices they are interested.
But thank you very much, Sotiris. Maybe before jumping to John, I'm not sure, Leila, if you have anything short to say here on this. We do have another question for you, which we'll come to as well.
Yes, well, I really understand the need for this testing. Actually, we are doing it for our own sensors, and we did it in the framework of our project for another sensor developed by one of our partners. But it does require a lot of effort to follow the strict guidelines for giving a certificate, let's say, which I'm not sure all the labs are willing to do, even though they do research on the systems. Yeah.
Thank you, Leila. John, you had your hand up. I'm calling
Yes,
you in.
very quickly. Sartorius is correct on AQSpec. AQSpec is for the manufacturers. They do it for free. The California taxpayer is paying for it. But there is some stress on Andrea Polidori now to start to charge for it because of things that are happening elsewhere in the USA. However, if you're a manufacturer, AQSpec is free and it's very good. And certainly you're absolutely correct. There is one secret you might try if you're a volume user. You might go to your local university and go find the atmospheric chemistry people and see if they can help you out. It won't be validation corrected. You won't get a certificate, but you will get some information back if you're friendly with them and they're friendly with you. That's the only bit of advice I could give.
Thank you, John. And it's very good advice there. Now we have one question for Leila, and then we'll have one question for Jan and John, and of course, Sotiris, if you want to come in and answer any questions. So for Leila, here in child health, could you comment a bit on how the exposure measurements carried out in your project are being compared or correlated to health data?
Yes, so I have to admit I'm not one of the groups that are working in epidemiological studies, but we do have an epi study in our project with 3 cities participating: Barcelona, Copenhagen, and Helsinki. So we are using low-cost sensors in schools, 10 schools per city, and we're correlating the data that we get for quality with specific outcomes related to respiratory health effects, absenteeism for children. This is an important parameter, and also cognitive cognition, so cognitive tests. And if you want more information, of course, I can direct you towards the partners in the project that are working with these studies.
Thank you very much, Leila. Now, Tian and John, are there published studies using body-worn low-cost sensors, especially CO2, to evaluate air quality and then address ventilation requirements? And then they say practical issues like where on the body they are worn, how to ensure air sampling is not interfered with, seem to be important. Short and sweet, if you don't mind. John, you first.
Yes, I know that Atmospheric Sensors built a portable unit for Frank Kelly's group. They're now at Imperial College, and they did a study like that. I've seen a few others. Mainly people tend to put them on bicycles a lot. The problem with bicycles is you ride your cycle behind a car, so all you're really doing is measuring the emissions of the car in front of you. But for a walking type, I think I've seen a couple of studies. I think Frank Kelly's groups is the most comprehensive. The problem is that you are shedding particles yourself and you are actually generating VOCs yourself. So are you measuring your environment or are you measuring yourself? Also, trying to keep a constant temperature is quite difficult in that way. I think that if you want to do something like that, you're better off putting them on cars or some other form of mobile transport and trying to monitor that way rather than on your personal. Even though personal exposure is everything, we really want to do it. It is very difficult technically because of the problems.
Thank you, John.
Yes.
Yeah.
Yes, I can fully agree. So we at Tropos, we run occasionally studies with instruments in backpacks, also with pupils, with school children. And there are probably some studies published, but you have to ask my colleague Jens Vogtländer, who is more involved in that. But yeah, short answer, yes, there are. And it's ongoing research.
Thank you very much for being very short and sweet there, Jan. Sotiris.
Yeah, there are some studies out there, but when it comes to carbon dioxide, it's very tricky because if you wear any device in front of you, it's going to measure directly the air that you exhale in, and those concentrations tend to be very high. So for these reasons, we recommend putting the devices on a backpack behind you.
And Leila, please.
Yes, so I agree for CO2 measurements and for ventilation regions. Maybe it's just better to have a fixed site monitor in the area, in the indoor environment that you want to measure. But for personal exposure to air pollutants, it's very, very interesting to have these personal monitors. Very hard. I mean, you want to have them in the breathing zones because you want to measure the air that this person is breathing, but then you also have the interference with what the person actually produces. This is why we tend to use them either in backpacks or lower towards the waist, which is not exactly breathing zone conditions, but you have to somehow, think about the problems and try to do the best. You know that the measurements are not going to be perfect, of course.
Thank you very much, Leila. So I want to give everybody one chance to say one more sentence from today. One sentence only. We'll start with our order. Sotiris first. Your one sentence to close today.
I think I will say what John said. I think we have to start trusting data from local sensors and not be so stubborn when it comes to accuracy. Accuracy is very relatively. If you think about the fact that we have been evaluating or correlating a health effects on human health based on outdoor sensors when we spend the majority of our times in the indoor space.
John, please.
Yes, I agree with Sartorius. Trust is everything. And I do like the idea that he said that we often are judged on the accuracy in peer-reviewed papers by academics who want to work relative to reference accuracies. And actually, these are indicative devices. And we should actually know what accuracy, precision, and accuracy together that we require and ask for that and not some theoretical high value that is beyond what we really require.
Leila, please.
Just say that low-cost sensors and monitors do have great potential, and the more we use them, the more we will understand their possibilities and their disadvantages, their limitations.
And Jan, the final word. Oh, your microphone, Jan, your microphone. Oh, we have some. Maybe you're going to have to write your last message, but it will stand the test of time. So, yeah, so if you could write your last message and we're going to head out. I'm very sorry that there was a little bit of but it will stand the test of time if it's written. So now is your chance to engage with the EDIAQI project. We promised you that this was coming. Please take our survey to support us in designing a household-friendly monitoring device for indoor pollution characterization. Scan the QR code and take the survey. I hope it works. I never tested it, so I hope it actually leads you to that. Yes, the slides will be all available for download, Mario. Don't worry, and we'll actually send them to you. Everybody who's registered will receive, obviously, in BCC. Now, we encourage you, lots of QR codes. I hope you have your phones out. We encourage you to become a part of our vibrant community by joining the In-Child Health Project, the EDIAQI project, and the broader Ideal Cluster community, along with various other initiatives for seamless updates and information. Please scan the QR codes displayed to follow our LinkedIn pages and to explore the websites of the In-Child Health Project, EDIAQI project, as well as the Ideal Cluster. So we're going to do this slowly because we have lots of different ones. We've stayed here for some time. Oh, I jumped one too much. Here is the Ideal Cluster social channels. Please join. And here is the EDIAQI social channels. Lots of them. Choose your favorite, choose your preferred social. And we extend our heartfelt thanks and gratitude to our panelists for their invaluable perspectives, to you, our audience, for the engaging discussions that brought this event to life. With that, we conclude today's session. Until next time, stay informed, stay connected, and wishing you all excellent air quality, both outdoors and indoors. Thank you, and goodbye, everyone. Thank you very much.